Okay guys, welcome back to Mostly Math. Today we are going to evaluate the Dirichlet integral by the method of Laplace transformation, where the Dirichlet integral is famously the integral from 0 to infinity with respect to some variable t of sine t over t. We're going to show that it's equal to pi over 2. You can typically use complex variables to show this relation, but there's actually an easier method which uses real variables by taking the Laplace transform of the integrand here, which we're going to do now. It only requires basic knowledge about the transform. We need to know the definition of the Laplace transform itself, the Laplace transform of some function of time, which is now going to be a function of some other variable s, is defined as integral from 0 to infinity with respect to time of e to the minus st times the original function. Should look familiar. And for this derivation, we have to know a few properties. We also have to know that the Laplace transform of sine of t is simply, making sure I write it correctly, 1 over s squared plus 1. And we're actually going to derive an identity as well. We are going to derive the fact that the Laplace transform of some function of time over time is actually equal to the integral from s to infinity with respect to some new variable s prime of the Laplace transform of the function of time without the dividing by t. We're going to derive this. Since this is not necessarily basic knowledge, this, however, is the Laplace transform of the sine function, can be found in any introductory text about the transforms or differential equations. For a brief summary of how to derive it, first you take the easiest possible example, the Laplace transform of the exponential. And then you just take the imaginary part, v to the iat, and that's basically the sine function. But we don't have to derive that here. It's pretty basic. Let's go ahead and proceed with the derivation. So you'll recognize some of the steps I'm doing if you're familiar with the Feynman's trick method. Richard Feynman, of course. His trick involves basically the same function, but there are a few more steps when you solve the differential equation. I think this method is simpler. The idea is to simply take the Laplace transform of the thing that you want to integrate and go from there. So we have the Laplace transform of our function we want to integrate, sine t over t, which would be a function of s. And I've conveniently written this identity here, telling us that if we know the Laplace transform of the function up top, and it's divided by t, we can simply integrate that Laplace transform to get the original function. But for clarity's sake, let's write out what will be the left-hand side of the expression. By definition here, this is just integral back to 0 infinity t e to the minus st of sine t over t. This will be the left-hand side of the expression. And also, using the identity over here, it's equal to the integral from s to infinity, respect to some new variable s prime of the Laplace transform of the sine function, which thankfully we have right here, very elementary knowledge of the Laplace transform. It's just integral from s to infinity with respect to our s prime variable, divided by s prime squared plus 1, which is an extremely easy integral to do. Any freshman calculus student will be able to recognize this as the inverse tangent of s prime evaluated at s prime equals infinity and s prime equals 0. Sorry, s prime equals s. That's the whole point of what we're doing here. Not all limits go from 0 to infinity. Sometimes they start at some other variable. And evaluating this, we obviously get pi over 2 minus inverse tangent of s. So we already have a pi over 2. But we have this other factor, which is not what we want. But that's pretty easy to get around here. We are now going to take the limit as s goes to 0 with absolutely no mathematical justification because this is an applied math video. If we take s being equal to 0 here, this will become the left-hand side of the expression, and this will be the right-hand side. We have integral from 0 to infinity, respect to time. S equals 0 here simply becomes 1 for e to the minus st. So now, the left-hand side tells us that the integral we seek, the Dirichlet integral, equal to pi over 2 minus inverse tangent of 0, which is obviously 0, since the angle that has a tangent of 0 is 0 itself. So this just immediately tells us, with no further calculation, the value of our Dirichlet integral. If you know a faster method of computing this integral, I would be curious to know it, since this is really slick, straightforward, and it's only a couple lines. However, what I do not think so straightforwardly is this identity, which was crucial in our derivation of this formula. I had never seen this before I worked on this problem, rather read the solution of this problem on Wikipedia, so I think it's important to know how it's derived. So let's go ahead and do that. If you don't want to know, you can feel free to stop the video. See ya. But for those that are curious, let's go ahead and proceed with the derivation of that fact. I need a new board for this bad boy. We're going to derive this now. Okay, so when I first approached this, I tried to start from the left hand of the expression, but that's actually more difficult than it seems. There's a way to do it. You have to differentiate this and then take the limit, similar to what we did earlier, but you have to solve a differential equation, I think, and it's messy. So I found it easier to start from the right-hand side. And just for future reference, I'm going to rewrite our definition of the Laplace transform here. Just for clarity's sake, this is all we need for this. Let's go ahead and start from the right-hand side, since it's easier. Okay. Well, we can see there's going to be a double integral, since the Laplace transform itself has an integral in it, so we're integrating an integral. So just go ahead and write these integrals. Right-hand side of our expression is integral from s to infinity with respect to some variable s prime of the integral from 0 to infinity with respect to time e to the minus st times our function to be integrated. Basically, at this point, the only thing that anyone could conceivably think of doing is reversing the order of integration, which proves to be successful. So let's go ahead and do that. This is equal to, gets a bit tricky, doesn't it? We're going to integrate with respect to time first, 0 to infinity. Keep our function of time along for the ride. Now we integrate with respect from s to infinity, new variable s prime. And, oh sorry, I made a small mistake here. There has to be an s prime of here, since this is the Laplace transform of s prime. F of t with respect to s prime. Okay, I'm going to switch the order of these variables here so it doesn't confuse me. Because typically we integrate, something like e to the minus 8x, and we don't write e to the minus xa. So I'm just going to switch the order so it doesn't confuse me. But they're of course equivalent. All right, this is an integral that we know how to do. So this is the entire point of switching it. 0 to infinity dt f of t along for the ride here. And this integral becomes e to the minus t s prime over minus t. So we can see how we get the division already. Evaluated at s prime equals infinity and s prime equals s. That's pretty straightforward. So this limit is going to be 0 because e to the minus infinity, of course, is 0. And we're going to have minus this. So minus minus is plus. We now have the result. It's just integral from 0. No. See, these double integrals are kind of tricky, aren't they? Right. Okay. Still there. dt, and now we have the f of t over, so we have e to the minus st. I'm changing the order of these variables here, and now we have f of t over t, and that is the answer basically. I just wanted to write it in this form for clarity's sake. And yep, this tells us that this is equal to the Laplace transform, or some function of time divided by time. The whole point of what we're doing. In a new variable, s. So that's it. That's the derivation of the identity. I think it's pretty straightforward, though you got to keep your variables straight and so forth. Don't get confused like me halfway through. But if you enjoyed this, want to see more math, please subscribe. See you next time.